Without further ado, without taking up any more time from this next panel, we're really excited about this talk. We're going to be pushing the limits, talking about advances in propulsion. This panel is generously sponsored by our all-day sponsors, KBR and Aerojet Rocketdyne and L3 Harris Company. And leading this discussion is Mary Beth Coble, the director of the Engineering Directorate at NASA's Marshall. Mary Beth.
I'm happy to be hosting this panel on propulsion today. And with me, I have Doug Bradley, Program Manager of the RS-25 engine from Aerojet Rocketdyne, Mark Fisher, Senior Director for Engines, Propulsion, and Fluid Systems at Blue Origin. He's an engine project manager, too. Eric Paulson, Senior Aerospace Engineer from AFRL. Tab Dodson, Program Manager for the DARPA Draco program. And Jason Turpin, the project manager for space nuclear propulsion at Marshall and also the deputy manager for Draco. So today we're going to ask our esteemed panelists a few questions, and they can talk about all the exciting work in propulsion. And I have to say, you know, I started my career in propulsion, so I'm excited to host a panel on this topic. So let's start with Doug. Doug, can you talk about what technology advancements you're making for the RS-25 engine in support of Artemis 5 and beyond?
Yeah, I'd love to do that, Mary Beth. First of all, let me start with where we are. If I can get I had to push this hard, so maybe I'm not doing hard enough.
Maybe point it at it?
No. There we go. All right. So where are we today? You're looking at a picture of the 4 RS-25 engines in the core stage of Artemis 2. That's at the MAF, at the Michoud Assembly Facility right now. That picture was taken just a few days ago. Now, you probably all know that these engines came from the shuttle program. RS-25s used to be SSMEs. The one on the upper right there actually flew 15 shuttle missions. The one next to it on the left flew 5. The 2 on the bottom, they didn't get a chance to fly in shuttle. We had 16 engines left over at the end of the program. But after that takes us out to Artemis 4, and then we're going to be done. And we're right now building new engines for Artemis 5. But they're going to have to be, those engines are going to have to be different. The reason the engines were chosen in the first place, or probably a lot of reasons, maybe 4 chief reasons: reliability, performance, flexibility, and availability. We had 16 engines. And so let's talk about the reliability. That was probably the key one. Reliability, first of all, foremost, for the safety of the crew, of course. Somebody said yesterday they think about crew safety every day, so do I. So that's very important. But reliability in the shuttle program had the added benefit of making them more affordable. You know, the one we flew 15 times, that engine was getting cheaper and cheaper the more we flew it. And the maintenance was getting pretty low, too. We've got a different vehicle now. Artemis, the architecture calls for expendable engines. I'm not the guy to talk about that. Let the mission architects talk about that. But what it means to us as engine makers is we've got to make them cheaper. They can't be as expensive as they have been. So how do you do that? You've got a really good engine that you're very happy with the reliability, and you're very happy with the performance, but they have to be cheaper. So I, like all good program managers, tell the team to fix it, but don't change it. So that's what we're trying to do. So some of the things we're doing are not high tech. For instance, we're looking at the processes that we take to build the engines. And we use a process called value stream mapping. A lot of you are probably using that, VSM, where you look in excruciating detail about how you manufacture the hardware. And you can really take a lot of, especially after you know how to build the hardware a lot, you can take a lot of waste out of that. Second thing we do is machines. The machines that make hardware that cut chips are a lot better than they were in the old days. I mean, it used to be you'd go from lathe to mill to boring machine, numerous setups, lots of chances for mistakes. Now we have machining centers. They'll do all of that in one setup. In some cases, we change the design. The main combustion chamber It functions the same, it looks the same, you wouldn't know the difference. It's made completely different process, even different materials. And probably the funnest one in my mind is the additive manufacturing. I bet you most of you in this room are involved in that. And so that's exciting. That's where we're cutting months out of cycle time to make hardware. And time means money in our business. So that's just a fantastic way of cutting cost. Now, how are we doing? That design work, those process improvements, they're done. And we've built hardware. We even are building some of the production units. But we're finishing off the certification of those. And we certify by hot fire testing. We can put an engine in a stand and test it very flight-like. And we test like we fly, and then even a little bit beyond that. We even test a little bit higher thrust levels than we need. I don't like to say that in an audience like that because there's a lot of vehicle makers and you guys always want more power. But we do test the edges. And so I thought just as an ending to this, I'd show you a little highlight film, 20 seconds of a 560-second test that we ran just last week, if I can get this to work. It turned black. Jay, help me. There we go. That's where we are, Mary Beth.
Great, thanks, Doug. Our next panelist, Mark's going to talk about engine development at Blue Origin.
Thank you, Mary Beth. I'm going to go ahead and get to my chart. All right, I'll go ahead and talk. Yeah. There we go. So Blue Origin has several exciting engine programs that we're working on at this time. We have 2 booster engines, one for our new Shepherd vehicle called BE3PM. We have another called BE4, which is the booster engine for both the ULA Vulcan vehicle as well as the Blue Origin New Glenn vehicle. There are an upper stage engine, BE3U, which will go on the New Glenn vehicle, and then we have our lander engine called BE7. The BE4, which I'm the program manager for the New Glenn variant, there are 2, one, for, as I mentioned, for ULA and one for New Glenn. They're very similar. They're about 75% common. There are different loads, and we'll talk about the reason why in a moment that the New Glenn vehicle is reusable. And so we'll talk about why that's so important to us. The BE4 is a 550,000 pound thrust, aux-rich stage combustion engine utilizing LOX and LNG. So why did we make and why did we design that engine? The stage combustion, as is with RS-25, provides efficiency and advantages in terms of ISP and also better utilization of propellants, which then means that the vehicle packaging can become more efficient. And so the choice of stage combustion seemed the correct answer for that. LNG has some interesting attributes. It's kind of got, you could look at it as the best of both worlds or maybe the worst of the worlds. I don't know, it depends on the day, but it's a cryo, which means that the density is pretty good, and again, that helps vehicle packaging. Not quite as difficult to handle as liquid hydrogen. Obviously, it is cleaner than RP and then provides the ability in terms of restart during the course of the mission, it's much easier to restart than an RP engine. The LNG has wide applications. What we learn in terms of the booster engines can be applied to our lander engines. And then, of course, in the future, in situ propellant utilization LNG is something that can be used for that in terms of using methane. It's also commercially available as a propellant. So it's fairly easy to get to and it's fairly easy to handle. And so those things made the choice of that propellant very advantageous for us. The reusable aspect was very important. As Doug mentioned, cost is king, right? So if we can learn how to reuse this engine, that is a key part of the New Glenn mission, is to be able to reuse these engines. With that comes an investment. We have to go through the testing, we have to go through the designs. You also have to go through the physical attributes of the design to be able to re-enter with a launch vehicle as large as New Glenn. New Glenn has 7 of these engines in the first stage. The ULA Vulcan has 2. So it's a large vehicle. We're going to turn that vehicle around and fire 3 of these engines and re-enter the atmosphere, and then shut them down. And then as we get closer to the ground, we'll ignite them and then land on a barge. So again, reigniting 550,000 pound thrust stage combustion engines on orbit and then doing it again is tricky. And this has been a huge part of the activity, the development activities that the team has been working on over the past couple years. So we have managed to restart the engine several times, 2 restarts, and following a mission profile, and that's been really exciting. But again, we're still trying to optimize those restarts. In addition to reusability, the last item I wanted to talk about, again, following with what Doug said, and that is the producibility aspect, the manufacturing capabilities that exist today. The use of additive manufacturing is a huge part to the producibility, but also the selective application of casting techniques, additive, and then traditional manufacturing is something that we work real hard on to find what are the right answers for that producibility. And again, and I'm glad you went first, he talked about cycle time, and it was funny because that's one of the things I worry about, right, is the cycle time of manufacturing these engines. We can't take 5 years or 6 years to build an engine. We can't really take 2 years. If we're going to hit rates and we're going to lower the cost of access to space, we've got to produce these engines, and they can't cost the moon, right? They have to be something that's achievable. And that takes investment. So it takes investment in the machines, it takes investment in the engineering. If we want to make them producible, we're going to have a cyclical development program. You have to learn, you have to be able to go to the next step and fix the problems that we have. And that gets difficult when you're building an engine of this size and, of course, meeting the requirements of, security launches and NASA launches, but it's something that has to be planned in, and that's a big part of the activities that we do. The engine currently has 30,000 seconds of hot fire time. We've delivered 2 engines to Vulcan, so the Vulcan variant is been flight delivered. The New Glenn flight engines are being built. I would say we had development activities all throughout last year. It was really exciting in terms of restart, and we have more development to go, and then we'll get into qual. The qual engine's being built right now. As we get ready to continue to build flight vehicles. The focus that we have today is on restart, being able to successfully restart efficiently and successfully and reliably to be able to land the New Glenn vehicle. And of course, that's going to help us lower the cost of access to space. There's a picture. You can see the stage combustion engine BE4 on its handler. And then next to it's a picture of it firing at our West Texas test site out where we launched New Shepard. We have 2 stands side by side for BE4. The really exciting thing that we're doing is we are building a development engine right now that will be used to hot fire at the historic 4670 test stand used for S1C. So we're about a month and a half away. The engine's just beginning final assembly. We tested that engine, which has 7,800 seconds of firing time on it. So it's a little long in the tooth, but it's gonna do well for us as we move it to 4670 here at the end of November, and then we'll get through activation and hot fire. So again, we're really excited about the advances that we've made with BE4 and what it's going to be able to do for us in terms of reducing that cost of access to space and the reliability of that engine. So that's
All right.
my presentation.
Thanks, Mark. Next, Eric, I'd like you to talk about something a little different, right? No more staged combustion cycle engines. How about, let's talk about the rotating detonation rocket engine technology and what's happening at AFRL, and maybe describe a little bit why those advances are attractive investment.
Sure. Thanks. So, yeah, I'm the program manager for the rotating detonation rocket engine program out at Edwards, California. That program started in 2017. It goes back, the idea of pressure, of rotating detonation goes further than that. It was originally thought of back in the F1 days, where they saw one of the instability modes was a tangential rotating instability, and it was pretty destructive in the F1 days. So that's why that's why we invented baffles to kind of put a stop to those kinds of instabilities. But people, even in '62, were saying, well, it seems like it's a very efficient combustion, that's why it's so destructive. Could we actually make use of it? And so there was a study done at University of Michigan to, I think that's the wrong presentation, but interesting study done at University of Michigan to try to see if they could demonstrate them. And the trick was they did all the theory behind it. It was a little early for the times technology to actually be able to repetitively test them. Was a little bit early, but we started the program in 2017. The main difference between a rotating detonation and a constant pressure or Brayton rocket combustion is our normal rocket, conventional rocket engines are constant pressure combustion. So it's deflagration. It's a flame, subsonic flame burning your propellants and expanding the gases as they burn. Constant pressure or rotating detonation or pressure gain combustion are all the same thing. Pressure gain combustion or rotating detonation are constant volume combustion. The gases don't have time to expand by the time that they are combusted, which means you get pressure rise at the time that they're combusting. So that leads to some interesting things. Thermodynamically, it means that you can get more useful energy or useful work out of the hot gas that you produce. So that leads to things like an ISP or specific impulse gain, so more thrust for a given amount of propellant. So that's very interesting. The other things, it's very fast combustion. Locally, where the combustion's happening, it's high pressure, high temperature. Locally, it's unsteady combustion, so that's different. But the combustion happens so fast, you can have very compact combustors compared to a conventional rocket engine, much shorter, and still get complete combustion. The other thing is it's already really an instability. So far to date, it appears that if it's operating as a single instability, you don't have a lot of energy left for normal rocket instabilities, which would be significant. A lot of the money we spend developing rocket engines is engineering those out of our devices. So there's several payoffs, including the ISP, where improved payload to orbit. So we've done a lot on computational fluid dynamics, actual experiment. It's been both modeling as well as experimentally driven. We're targeting 1 to 5,000 pound thrust devices because that overlaps with the current interest for the Space Force and AFRL's mission, which is tactically responsive space. And so there's a lot of engines out there in the 5,000 pound thrust class for small vehicles that if we could give them an engine that performs better, they might be interested and they're risk tolerant. So that means there isn't so much pushback on, yeah, but I don't know everything about it so far. Okay, that's about it.
All right, great, thanks. Next, I'd like to introduce Tab Dodson, and she's going to talk about the DARPA Draco project. And could you talk also about what the goals are and why DARPA is interested in pursuing those goals?
Sure. Okay, so you see on the title slide here, there are a few logos. Besides DARPA, there's also NASA and Space Force. So Jason is the NASA part of the partnership. Space Force is not here to speak on their own behalf, and so I will be brief in sort of saying what their potential mission pull might be. But when it comes to DARPA, there are at least a few unique pools or roles that this agency has in terms of interest in doing this mission. So one, it is DARPA's charter to create technological surprise and to prevent technological surprise from being incurred upon the country. And so a lot of people may know this already, but DARPA was created in response to the launch of Sputnik. And so a lot of the programs that DARPA does can be thought of like Sputnik moment type programs. And so think back to what it must have been like during the time of Sputnik, when we had no man-made spacecraft sort of orbiting the Earth, kind of like how we have today. Sputnik was a very incapable kind of tin can sort of device, but it did demonstrate that you could put a satellite into Earth's orbit, and it ushered in a new era of spacefaring satellites and other sort of spacecraft. So that is one of the reasons why this sort of mission is so appealing to DARPA as an agency. And with that, you know, DARPA, it's also our charter to go fast and build hardware as soon as possible. And if the program after a year and tens of millions of dollars hasn't built any hardware, then the agency has to ask itself, well, is this really a DARPA program and worth DARPA's investment? So another thing that pulls DARPA into this kind of program is it's also in DARPA's charter to make big bets. We're kind of like the Vegas of the government. We're charged to make very risky, high investments and high risky things, and expecting that there might be a high payoff. So in this case, the high risk bet that we're making is that we can go straight to space with a demo. And that's because we're relying on the fact that there was at least 2 decades worth of nuclear thermal rocket testing done already that brought this technology to a state of flight readiness. And so that's why we're banking on this risk, and also the fact that these ground test infrastructures don't exist. So that's a risk that we put that bet on the table, and we asked our government potential transition partners, do you want to put a bet down on the table too? And then they said yes, obviously. So the last thing, the last sort of thing that makes DARPA's participation in this demo unique and why this demo is possible is, according to the Atomic Energy Act, the congressional legislation, historically only the Department of Energy and Nuclear Regulatory Commission are authorized to procure and operate nuclear reactors. And so that might be an answer to a lot of people's questions as to, you know, why aren't we flying a lot of these nuclear reactors in space already? And it's because typically the DOE and NRC are the gatekeepers for who gets to buy and operate nuclear devices. And so DARPA got the unique blessing, if you will, from the DOE to have its own safety and authorization basis. And so that means that we are able to operate quick and agile and set our own rules and regulations. Of course, we still consult with the DOE and NRC for their peer review, ask their opinions on things, but we're not beholden to sort of find me the rock kind of exercises. So and again, I guess, you know, Jason's here to speak on NASA's behalf, but when it comes to the Space Force and their interests, so the sector of the Space Force that's funding Draco's launch vehicle, they're the same division that's standing up the Space Access Mobility Logistics Division. So you might ask, well, what is Space Access Mobility and Logistics? So we like to draw parallels to how the DoD does things in the sea. So think of how logistics is done in the ocean. So right now in space, we have boats that are, you know, CubeSat size, like, you know, RC toy sort of boats. We have boats that are jet ski size in space. And then the biggest boats that we have in space are like the school bus size, and those are like your personally owned fishing kind of boats. We have one Magellan class ship, and that's the space station. And so when it comes to getting around in the ocean, you can't get from across the ocean very efficiently on a jet ski or a personally owned fishing boat. You need a big ship with big engines. And so that is really where the appeal of the nuclear thermal rocket comes in, is we want to cross the ocean between the Earth and the Moon. We could do it in a small boat. It would take us forever, and we wouldn't have a lot of power to draw from to keep our astronauts and things alive. Or we could use something like nuclear propulsion, which is what the Navy prefers to use in the ocean. So that is what the vision is for space access, mobility, and logistics in space. With nuclear propulsion, you can think about it the same appeal as it has in the seat. Okay. So the actual Draco program. So the one thing that makes us unique from the past programs, Never Rover program, is that we're using high-assay, low-enriched uranium. And so you can think about the Draco program like the next engine test in the test series which came before it. So every Never Rover program, they changed something about the engine. So they changed the flow paths, they changed the startup techniques, maybe they changed some valve positionings, and then they measured the effects that change had on the engine. So because the high-assay low-enriched uranium is the biggest change as compared to historical engines, this is going to be our greatest focus in this demo. So the primary focus of the actual demo is going to be on the criticality experiments. So before you start the engine, so the thing that makes gas come out of the nozzle, we are going to turn the drums around the reactor, bring the reactor to a state of criticality, low power, warm power, et cetera. And then once we get enough data, we'll declare mission success and update our flight software and attempt an engine startup. So again, mission success is defined by getting enough data on the HALO reactor. That's what makes this mission unique. This is a little cartoon of what the demo is going to look like. We're going to at least 2,000 kilometers circular. That is what the Space Force prefers, and that's in compliance with orbital debris mitigation standard practices. We will, again, conduct a series of reactor experiments and attempt an engine startup. We are allowing the performer to test at the lower ISP range. With the objective of, again, collecting as much data as we can. This last slide just should give you an idea of where we are in the program. So a year from now, we're going to be doing a series of engine component tests. We're looking at doing those tests at NASA. Sort of local to here, NASA Marshall. So that's the turbo pump, the boost pump, maybe the nozzle, and the reactor, of course, the main element of the engine. But the reactor will not have a uranium, so it'll be what we call an EDU reactor. And so that'll be coming up soon. After 2 years, phase 2 will end. And then once we have a final design, we'll start putting in the uranium into the reactor, integrate it with the stage, and launch it out of Cape Canaveral. March 2027 is what we're targeting right now. And I guess that's the overview of the Draco program. I'll turn it over to you, Jason.
All right. Thanks, Tab. Jason, can you share what NASA Marshall propulsion advances they're pursuing in support of Draco, and also give us some context to how this mission fits in with the broader goals of your S&P program and STMD?
Sure thing. Hey, I just noticed coming in here and meeting these folks on the panel today, I thought I'd mention it. I joined NASA Marshall in August of 1999, so about 23 and a half years now. Worked propulsion 17 or 18 of those years, then moved on to work human landing system for a couple years, and now doing this great nuclear propulsion gig. And when I first hired into Marshall, Mr. Mark Fisher was my first boss, my first branch chief at Marshall, which was pretty cool. And Mary Beth Coble ended up being my boss and my boss's boss and my boss's boss's boss along the way, which was pretty cool. And then I've had the great opportunity to work multiple Oxford stage combustion class engines over the years, supporting and helping both Blue and Aerojet Rocketdyne and lots of other companies. And now I'm doing nuclear propulsion for NASA, partnered with Tabitha at DARPA, and I just thought, man, that's pretty cool last 23 years that I've had here. So just really thankful for that to start off with. So I thought I will get around to answering the question quickly about, why nuclear propulsion in Mars, but I thought I would just start off by big picture, why is NASA, why is the U.S. government, why is NASA interested in nuclear propulsion? It's ultimately, from a NASA perspective, we want robust and enduring access throughout the solar system. And I think that's kind of the vision for this program that I'm running at NASA, which is the Space Nuclear Propulsion Program. And so that's really what we want. And in order to really have that, especially for out to Mars and past Mars class missions, you really have to have higher performance in your propulsion systems. There's a great book I read a couple years ago. I can't remember the title exactly, but it was something like 10 great engine programs at Pratt & Whitney. And one of the chapters in there was titled RL-10, Our Only Moneymaker. And this was an old book. And it's from a long time ago, but it struck me when I read that we're still flying versions and variants of the RL-10 today, and it is a fantastic, fabulous, high-performing LOX hydrogen expander cycle engine. But the collective community, have been tweaking the performance of that engine over the years, and we're just you kind of get to this asymptotic place where, for chemical propulsion, you're tweaking for 0.25% of nozzle efficiency or 0.25% of combustion efficiency to try to just get a little bit more out of these already, Cadillac high-performing Ferrari kind of chemical propulsion engines. And what nuclear does for you, even though we're much more immature in terms of fielding these types of engines, what nuclear does for you right out of the gate is the kind of engine that we're talking about developing for the Draco program, for instance, which is just the first prototype. It's a prototype engine. It's not 50 years of progressive development on an engine. You're talking about almost doubling the kind of performance that you would get out of these traditional chemical rocket engines. And so, although I love stage combustion rocket engines, and I know, these guys didn't really talk much about how complex and complicated those engines are to develop and what it takes to get through a successful development program with those engines. What you're talking about with the capability of nuclear is basically being able to come out on the floor, not the ceiling, not after 50 years of work, but come out on the floor and be basically, for nuclear thermal engines, double the performance of what you would get out of a traditional chemical rocket engine. And so that is the allure. That is why we, NASA, why DARPA, why the government is interested in pressing the pace and developing those technologies, because that's where you start. And then you can imagine if you could just get there and then work that and tweak that for the next 20, 30, 40, 50 years, where you could end up is truly amazing from a performance perspective, and it does really begin to enable this robust and enduring access throughout the solar system. So that's really why we're about nuclear propulsion and why it's kind of exciting to be a part of that field. So from on the chart, from a crewed interplanetary mission perspective, that performance buys you a lot of things. It buys you reduced transit times for planetary missions like Mars, which means less time for the crew to be in transit, more flexibility for the types of missions you can do, more contingency planning options. You can start to look at seriously at like engine out scenarios and things for Mars missions when you step up to nuclear propulsion class kind of performance. So it really helps a lot there. And so that, from a crewed perspective, crewed astronaut perspective, doing interplanetary travel stuff, it makes a whole lot of sense. But then you can flip it around and say, well, what about just deep space science exploration? When you get out past Mars and you don't get a lot of energy from the sun, I'm sure some of you have seen that, when you start looking at how the power falls off from the sun and what you have to do from a solar array perspective, once you get out past Mars, it goes down rapidly. And so you're starting to need other kinds of power available on spacecraft. And we got a community of scientists in NASA that are awesome, but they're used to fighting for 250 and 500 watts of power to go do missions produced out of radioisotope thermal generator kind of power systems. And now we're starting to think about, well, what if we had nuclear propulsion, nuclear electric propulsion, and we could couple that and produce, instead of 250 or 500 watts of power, now you have 10 kilowatts of power or 20 kilowatts of power. Well, it's a whole different way of thinking. It's almost like taking a designer that's been working on turbo machinery shafts their whole career, and they know they got to start with a forging out of this material, and then they got to do this process and this process and this process, and then all of a sudden you say, throw all that out the window. I'm going to give you this fancy 3D printing machine, and you can just print almost whatever shape you want. Now, how would you design that part? It really takes a whole different kind of mindset, and so that's why we're excited to be doing nuclear propulsion. That's why the DARPA opportunity is such a great opportunity for us from a nuclear propulsion perspective, is because oftentimes you have to balance a lot of things when you're early in the development phase for systems like this. There's, on the one hand, you've got a lot of technology that you got to go kind of increase the maturity of. You got really low maturity levels on the kind of materials that you're going to use for fuels or moderators, or the different high temperature materials and elements that are in the reactor that are a challenge. And those are fundamental kind of traditional engineering science kind of work. You just got to go do a design of experiments and run through a whole bunch of stuff and just work that until you can get it right. So that's the left side of the spectrum. The right side of the spectrum is, what does it take to integrate all that into an integrated system and get it to work? And it turns out that problem is just as hard or harder than that technology maturation problem. And so from a NASA perspective, why we were so interested in partnering with DARPA on Draco, for instance, is because it was an opportunity to simultaneously kind of advance some of the tech maturation that we'd been working internally with industry, with DoD partners, with Department of Energy partners over the last 3 or 4 years, and couple that work with the integrated system aspects and what it's going to take to really go put a system together and fly it and get that integrated set of test data that will hopefully lead to the next operational system downstream. Both sides of that spectrum is important. Well, with the fiscal realities today, it's really hard for any one entity to go kind of bite a lot of that off with everything that everybody wants to do. And so one thing this partnership did for NASA was provide a place where we could resource share to go have synergistic goals, to go put stuff together as a system, go get real data as a system, and push the envelope that way. And so that's a big part of what we're doing on Draco. I think one other thing I'll say, and I know I'm kind of going over time here, is Tab mentioned this low enriched uranium that we're using for Draco. Well, that's a decision that NASA, I think Mike Houtz is in the audience here. He kind of forced our hand, I think 3 or 4 years ago, before my time, and pushed us away from looking at high enriched uranium fuel for nuclear propulsion to this low enriched fuel, which was probably a strategic stroke of genius, because there's a little bit of mass penalty that comes along with that decision, but doing that gets you away from proliferation concerns. It gets you out of Cat 1 kind of nuclear facilities, gives you a lot more flexibility in how you do development, and also there's a lot of synergistic overlap between that fuel type and what industry wants to do for the microreactor industry that might be coming along, hopefully in the U.S. and across the world at some point in the future. So it starts to tie a bunch of different stakeholders together, gets a bunch of people interested in moving the ball down the field, which is what it's going to take to do something like nuclear propulsion in the long term. Just real briefly, the Space Nuclear Propulsion Program at Marshall is primarily focused on fission-based propulsions, and so we classify that into nuclear thermal propulsion and nuclear electric propulsion. We're adamantly pushing forward and trying to make progress in both of those areas, and both of those areas have advantages and disadvantages depending on the mission space and what you want to do. And kind of the ultimate goal is to think about combining those two things, where all of a sudden you can take a single kind of reactor system, generate high thrust, high fuel efficiency performance, but also generate electrical power on the spacecraft. And so that's really kind of what we're about at Marshall or NASA doing that.
Okay, great. Thanks, Jason. I have a few more questions, or is there one from the audience we want to start with? Oh, Eric's presentation wasn't up earlier. Okay, Eric, why don't you show a little bit about rotating RDRE?
One thing different about RDREs that I didn't mention. The one thing I didn't mention about RDREs is we use annular combustion chambers. So if you think 2 soup cans nested, slightly different size, in between the 2 soup cans is where we're combusting. So that's where the gas and fuel is being injected. So you can see a large eddy simulation CFD of a methane oxygen RDRE, 3-inch, about 200 pounds thrust that we used for the first couple of years to do both validation of the CFD as well. So you see 3 waves spinning around. The injectors are on the bottom. The gas exhausts out the top in the lower right-hand side. And so you see three rotating detonation waves spinning around, combusting the gas in that first less than an inch. Matter of fact, it's about a ½ inch in that 3-inch device. So a very compact combustion zone. The blue in the foreground, when it comes around the front of that cutaway, is the high pressure region of the gas. So that contains kind of where the detonation is happening. And then you have the gas expand, go pretty much axial, and then goes out the upper side. That 3-inch device on the top right is the parallel experiment that we use to do model validation verification. So our main focus is to go fast. We kind of got everybody aligned, working with government, academia, industry, and we said, okay, this is where we want to be. This is our first tech transition, and everybody pretty much lined up. You know, if you sprinkle a little money, people respond well. So we said, this is where we want to be, and everybody pretty much aligned with that, and we've made some really amazing progress in a very short amount of time. Again, our first LOX liquid methane test at Purdue for a 5,000-pound thrust chamber was in 2021. Since that time, we've done LOX kerosene injection. They work really well with liquid injection. And our focus is to enable a space access demo in the very near future, so FY24 plus. Next slide. Oh, all right. So yeah, the 6-inch one on the bottom left is our 5,000-pound thrust class that was first tested in 2021. Bottom right is a 2-inch heat sink device. The center body is material coupon, so we made the whole center body our material coupon and tested it and tried to break it. That's a particularly well-performing CMC that we're very interested in. We want to demonstrate the specific benefits of compact combustion, ISP gain, where we can either trade it for, if we got to inject it at lower pressure and get the same ISP, that potentially simplifies our turbopump assembly, which are a high-cost component on liquid rocket engines. Or you can just have the state-of-the-art turbopump assembly and try to get the high ISP out of it and have some, larger payloads for a given system. And then if we can control combustion instabilities, really, I think that everybody will be knocking at our door if that comes true. To date, we've seen nothing but positive reinforcement that appears to be the case, at least at this scale. Scale is everything in instabilities, but we're leveraging technology. It's unsteady combustor injector nozzles. That's all new. We don't do unsteady devices, although when interesting things happen in a rocket engine, it's because things have gone unsteady. Thermal management is a challenge. That's the piper we pay. You've got a 5,000 meter a second detonation shock wave spinning around your injector face. That's a thermal management challenge. It's a very small region you got to keep cool that's scrubbing the wall. So thermal management is a key technology challenge. And then the tech needs specifically that Space Force have asked for is lower launch life cycle costs. Turbopump assemblies are a big piece of that. Shorten the development time for rocket engines. That's turbopump assembly is a big schedule driver. And then combustor stability is also a big schedule driver for rocket engines. And then improve the engine integrated ISP, not just the chamber. So when you put it into a full integrated engine with, power head, nozzle, what kind of an ISP gain can you actually achieve with these devices then? Okay, that's pretty much the points.
All right, great,
Thanks.
thank you. So you've heard a lot from our panel about budgets and how to make propulsion cheaper. Doug, can you talk about, with all the advancements we'd like to do in propulsion that have been talked about today, how we can, what are your ideas for making things more affordable so we can afford everything we want to do?
Yeah, that's a great question. I mean, we're working in limited budgets, and how do we change things and make them more affordable? You start out with, I think, achievable but significant goals specifically for the RS-25. Our NASA leadership knows that that's a struggle, and you don't want to change things too radically, or you need to spend a lot of time testing them. So they gave us a goal of cutting 30% of the cost of the engine out and keeping the reliability and performance the same. And so that seemed reasonable and achievable. And we are achieving that. We check that on a weekly basis, and we're counting every hour it takes. So how do we do that? Actually, spoiler alert, we've got some designs on the table working with Marshall that we think we can get 50% out, but that's a discussion for another day. So I talked about VSMs, for instance, value stream mapping. That's cheap. You know, if you're on a limited budget, you're using the people that are already on your program, looking at processes that you're already doing. You're just making them better. Now, there's a couple of things you want to do. When you do that, you want to pick the right team. You need a cross-section of individuals, engineers, manufacturing people, quality, hands-on, analysis people, rookies and veterans, very important. So that helps that. You also want to walk the process. I tell my teams, because this is the way I learned it, you need to become the part. You go through that whole process as though you're the part. Even if it means bouncing back and forth 10 times between two departments, you force yourself to do that. Then the next thing we talked about, or I talked about, was the new machines, the new and improved machines, modernized machines. That's kind of a company investment. Doesn't cost the program anything per se. You can't just drop them in the factory. We just got done with a multi-million-dollar factory expansion project, and we moved all the pieces of our machinery around in the factory like I don't know, like pieces on a chessboard. You need to optimize that and be smart about it. And then the 3D printing, I just love that. I get mesmerized by watching the lasers go to work. There you have to pick the right parts. First of all, it's not a solution for every part. And secondly, it's all about material properties. That's fundamental to design. So you got to pay attention to that. Internally and on the surface, 3D parts are different than castings and forgings. I mean, I'm preaching to the choir. You guys know this. So you have to spend some of that funding, those precious dollars up front to really characterize your material properties. And it's gonna pay in the end. You don't want to get downstream and know you don't have the proper material properties. So, you know, there's 100 other things, but in a nutshell.
Okay, great. Thanks, Doug. Are there questions from the audience, or I have some more? Oh, I guess there are.
Okay, thank you. I have a question for Mr. Bradley and Mr. Fisher. So both of you are designing an engine that was first designed to be reusable. So what are the challenges of taking those same engines, the BE4 on New Glenn and the RS-25 on Space Shuttle, and putting them on expendable rockets such as SLS and Vulcan? Thank you.
You know, it is something that we work on a lot. Some of it has to do with making sure that, since we do have two customers in our case, that we make things common, which really helps reduce the cost. But we also look to find the optimization areas, the way we start the engine in an expendable and versus a reusable is very different. And so, again, we don't want to put the expensive systems on the expendable that we do need on the reusable, but we don't want to make them so different that they become snowflakes, right? And so, you know, that development process takes time, but in the end, it kind of pays for itself, because then, and that's why the variants, and I talked about the two variants, you know, they started out very similar. Matter of fact, inside the turbopump, the two engines are they're identical inside the turbopump. But it's the outfitting of it that we focused on to make them more efficient for the particular application. And therefore, when they become more efficient, they become cheaper, and therefore the best answer for both of those two different environments.
Yeah, that's a great question. For us on the RS-25, to hear, you know, Mark talk, I think our job was a little easier than yours. Our mission for shuttle was very similar to Artemis. It's a stage and a half, right? We start at sea level, we shut off in low Earth orbit. So the overall mission was very similar. And going from reusable to expendable is easier than the other way around. So in some cases, we took advantage of the fact we're going to be expendable, and we can get some cost savings there. But we did have the first part of the program was called the adaptation program, where we had to look at the different rocket that we were fitting this engine into. And so there were differences. For one thing, we're a lot closer to those big solid rocket boosters, and those things are nasty. And so you really have to make sure that you use some insulation and protect the engines from that. The engines are starting a little bit differently, but we had a lot of flexibility, so that wasn't much of a challenge. The one thing we did do, though, we did redesign the engine controller. That's the onboard computer that controls what the engine does. That needed a redesign. I mean, it was 15-year-old computer technology who's got a 15-year-old laptop on their desk. So that just made sense to do that. So I think in a lot of ways our job was easier than Mark's, and it was a little bit more straightforward.
Okay, there's a question down front.
Okay, all right, it's probably directed to Turpin. And this is probably stemming from a systems integration perspective. You spoke about nuclear propulsion, and a lot of disciplines are going to cross-pollinate, and a lot of stakeholders with respect to heliophysics, with respect to a number of disciplines. And my question is, have you experienced many challenges from a cybersecurity perspective, given, compromise can happen at the ground, the user, or even at the space segment? It would be interesting to learn about that.
Yeah, so that's something that we certainly are addressing on both the NASA, and maybe Tabitha can talk about it from the DoD side of the house. Just system security in terms of uplinks and downlinks and protecting all of that data and what you encrypt and what you don't encrypt, and just all the planning and processes that you have to follow in order to go do really any mission, but certainly a mission like this or the Draco mission are paramount. And so that's built into our plans and processes. We have processes for following things to ensure that we're doing the right things in those areas. Probably just leave it at that. Maybe, you brought up system integration too, that's one aspect. I would just say that, for the students that are in the room, integrating complex systems is one of the most challenging jobs there is in engineering, and cross-pollinating between a lot of different disciplines and a lot of different stakeholders is extraordinarily challenging, extraordinarily rewarding when you can do it and do it right, but really staying focused on communication skills, and maybe even having a little bit of salesman or saleswoman in you to be able to communicate ideas effectively. And I mean, when you're standing in a room full of 100 people who all feel very strongly about something, and you're trying to push your idea across, it's a challenging environment, and it takes some getting used to for some folks. And so it's a very important discipline to everything that we do.
Up top.
Hello, this is for Mr. Turpin. The question I have is regarding, is the biggest focus on current development of nuclear electric propulsion more focused on the electric propulsion side, or more focused on the converting nuclear power to electrical power side at Marshall as well as other agencies?
I think just the summary of the question was, what's the focus from a nuclear electric propulsion perspective? Are we focused more on, say, the actual propulsion element that's generating the thrust, or the power generation or the power conversion type of elements for nuclear propulsion? So nuclear electric propulsion is one of the major subsystems that we're pushing at NASA. Nuclear electric propulsion is all about taking thermal energy that you generate from a nuclear reactor and effectively converting that thermal energy into electrical power, and then taking that electrical power and doing something useful with it. In the case of nuclear electric propulsion, it's using that electrical power to power electric thrusters that generate super high exhaust gas, really, small thrust, but really high exhaust, and give you a really high ISP or performance, really high fuel efficiency. So, a traditional chemical in-space engine might be, the measure that we give there for ISP might be 450 seconds. Step up to nuclear thermal propulsion, high thrust, we might jump that up to 900 kind of seconds of ISP or fuel efficiency. And then when you start getting into the realm of electric propulsion, your thrust level goes down, but your efficiency goes way up. And then you start to talk about 2,000 kind of seconds. And so it's very important for some set of mission spaces. But in order to do that, you have to effectively be able to convert that thermal nuclear power to electrical power and then ultimately to thrust. And so finally getting around to answer your question, I think we have what we call a technology maturation plan at NASA that really outlines and defines how we invest and what we want to mature from a nuclear electric propulsion perspective. And it bridges all of those kind of component capability subdisciplines. And so we're actively investing and pursuing in all of those elements, not just one or the other.
Okay, I think we're out of time for today. So thanks for your attention, and thanks for our great panelists sharing what they're doing in advancing propulsion.